Hello, everyone. My name is Elena. My teammates are Sumit, Aditya, Aditesh, and Jen, and we make up Team 11. This is our agenda for the presentation, starting with an introduction to our project, discussing our objectives, methodology, results, and conclusions. Now for the introduction to our project. Our project was to utilize multiple robot agents to map and explore an area autonomously. By using more than one robot, the complexity increases, yet the efficiency can be increased as well. Efficiency comes with having different areas of the environment explored simultaneously. Avoiding obstacles that other robots have sensed can decrease issues as well. With multiple robots, one of the main benefits is having reduced runtime, and having the maps merged in real time can add other benefits. There's a lot of prior work in terms of multi-agent SLAM. These two papers helped us get a solid foundation for both the autonomous portion and the map fusing portion. We added to existing work to test the initial pose optimization in different environments and merge the local maps better.
The objective of our project is to basically implement utilizing multiple robots and at the same time ensuring map fusion between the individual maps created by each of the agents. In addition, we also aim to empirically derive general optimization initial pose locations of robots in the environment to optimize the overall mapping time for the global world. Also, to ensure efficient merging of individual local maps, we employ feature-based matching using standard OpenCV algorithms to generate the global map. For the methodology part, we implement a ROS framework that mainly consists of 4 ROS-based built-in packages, as you can see on the right, in which for mapping and localization, we utilize the SLAM G mapping package that uses a modified version of the standard particle filter algorithm. Exploration of the environment takes place utilizing move base and explore light packages, and then we utilize the multi-robot map merge package to then combine the individual maps to complete the global mapping.
So as seen from the earlier slide, you saw that there was 3 turtlebots, but this is a ROS framework for one individual turtlebot. So basically what happens is the turtlebot sends a ROS message from its sensor measurements, such as the LiDAR scans and odometry. And these LiDAR scans are later used in the SLAM G mapping package to generate a map which represents the robot's current understanding of the environment. After the generation of the local maps, these local maps are later sent into 3 maps, as Sumit mentioned earlier, the map merge, explore light, and move base. So in the map merge package, as seen from the top part of this slide, each local map from the turtlebot are added to the package so that all of them are merged to the package while the exploration of the turtlebot is happening simultaneously. And this local map are all merged into one global map, as you can see on the right. And simultaneously in the move-based package, this builds an occupancy grid map of the environment. The package utilizes the robot sensor and odometry data to create a local and global cost map based on these features that the robot detects. Each grid cell of the occupancy map basically represents a probability of the traversable cells in the environment and identifies features such as obstacles. The global cost map basically represents the robot's current understanding of the entire environment, and the local cost map represents the robot's immediate surroundings, which is being updated in real time using the robot's sensor measurements. Once the global cost map is set, then this gets updated through the Explore Light package as the package identifies more unexplored areas of the robot through sensor measurements. And during this process, the package determines a goalpost to those unexplored areas. This goalpost to the unexplored areas later gets sent back to the move-based package, and a trajectory is planned from the robot's current location to those goalposts. Once the trajectory is determined, then a desired command velocity for the robot is determined, and that is sent back to the turtlebot. And this process is continuously repeated until all the areas in the map are explored.
So we initially started with the basic room environments that we can see on the left, where we observed if the initial pose changes affects the global map completion time, and it does affect it significantly. And on the right side, we can see the house world, which is where we conducted most of our simulation work and derived our conclusions from. Next slide. So here we can see the real-time simulation of our map merging. These videos showcase the active multi-agent map merging happening in stage 2 and stage 4. The global map is generated only when 2 or more agents have local maps that show significant overlap for a certain area. Once that area is detected, it is added to the global map. So here we can see the final global maps for 3 different initial pose patterns. The initial positions of the bots are depicted in the green circles, whereas the time of completion is denoted underneath each image. As can be seen from these images, having bots close to each other with significant overlap in the map results in a faster completion time, whereas starting from different regions can cause the completion time to increase. The bots that were significantly closer took like around 12 to 13 minutes, whereas the bots which were far apart took 17 minutes to complete the whole global map. And for the case where we use a 6 agent for simultaneously mapping the same environment, it is observed that the time for completion is significantly less. It's about 50% less as compared to the 3-bot system. The map which might appear over here as good is not really reliable, as we can also see the walls are not really properly aligned, which can cause some interferences. So this can be improved with the method that will be discussed further down in the presentation.
So apart from using the multi-robot map merge package, we also created our own pipeline for map merging using OpenCV. The map arrays were converted into first image files and then were processed with OpenCV. If we found a considerable matching, which is decided based on the distance between corresponding points features in the two maps, the map merging pipeline would be able to merge those two, else it will discard those. We extracted key points in both the images and then used a FLAN-based nearest neighbor matcher that matches these key points. After that, we computed the transform between these matched key points using the ransack algorithm. Can you move to the next slide? Some conclusion and future improvements are here. So one is that the initial position of the robots is significant to reduce the mapping time and the quality of the merged maps. Using our experiments, we found that for maps generated with a fewer number of robots, it is essential to consider the layout of the environment and spread the robots for optimal mapping. For less robots, it was found that it would be better to start with some initial overlap. But for more robots, we could start with different rooms to get the minimum amount of merging time. The map merging was also successfully implemented using OpenCV based on feature matching and obtained an RMSE-based accuracy of 88%. Some future works that can be done are to get a better merging algorithm or to use point clouds and also to test the algorithm on real robots. This concludes our team's presentation and we are happy to answer any questions that you may have.
I think that was